All right, so it's 5 o'clock. Let's go ahead and get started on this problem. We sort of started on it last time, but we just started the intro. We didn't really get through it. So example 8 was find the derivative dy dx if I have the function y is equal to 17 to the x power. And then let's say I want my final answer to not have any y's. I want to make sure my final answer only has x's for us to work with. So what was that first thing that I did last time? What was the first step on how I started this problem from the previous lecture? If I was looking at y is equal to 17 to the x.
You set both sides to multiply by log.
Yeah, so in other words, what we did last time, or what I did last time, was I took the natural log of the left and the natural log of the right. In other words, instead of having y is equal to 17 to the x, I wrote the natural log of y is equal to the natural log of 17 to the x power, like so. And the reason why, well, two things I want to mention about this. The first thing is that I'm still allowed to do this, particularly because, one, from algebra, we know if I do it to the left side, as long as I do it to the right, then generally we are fine. And then if I want to be a little bit more nuanced, the other reason why I'm allowed to do this is that we know that we can't do natural log of a negative number. But if I look at 17 to the x power, that's always going to be positive no matter what. Whenever you take 17 to any power, it's still positive. So I'm not breaking any rules about accidentally taking the natural log of a negative number. All right, so the reason why I wanted to do this is that now I can apply the property of a logarithm. I know for logarithms, I can take that power of x on the right, and I can bring it to the front. In other words, I can write natural log of y is equal to x times the natural log of 17. I have not done any derivative work at all. All I've done was apply the property of logarithms. After this, I claim that now we can know how to deal with this. We can do some implicit differentiation. I know it's implicit because I don't have just a plain y is equal to whatever. So I have to use implicit. Let's start on the right side first. We'll talk about the left side in just a moment. So on the right side, I have x times the natural log of 17. What is the derivative of that expression? Well, first off, if I look at natural log of 17, that's just some random number, some decimal value probably. So really, I have a number times x. So what's the derivative of this number times x? What was that? Not 1 times, well, technically, yes. Because if I told you the derivative of a 3x, you would tell me 3, right? Same thing here. Is that this one's not a pretty number, like 3, 4, whatever fraction. So on the right, my derivative is just the natural log of 17. The same idea as if you had 3x, the derivative of 3x would be 3. Here, we still have a number times x. So by a quick power rule, we have on the right the natural log of 17. Now let's go ahead and talk about the left side, and you're going to see why I saved this for later. The derivative of the natural log of y. So if I want to be a little bit technical here, I am using a chain rule here. What is the outer layer of this function? There will be a dy dx somewhere in there. But right now, just the outer layer of this function is the natural log of something, right? And then my inner layer is y. Does anyone have a guess on what the derivative of the left side of my equation will be? Well, let's see. What's the derivative of a natural log? Yeah, 1 over x, or in this case, we have 1 over y. Oops. 1 over y. That's the outer layer. What's the derivative of y? Yeah, dy dx, or if you want, you write y prime. They're both mean the same thing. This thing keeps on lagging a little bit. Dy dx. So the 1 over y comes from the natural log. The dy dx comes from the derivative of y, technically multiplied. Well, on the right side, it's a little bit more complex here. This doesn't have any x's right here, so it's a coefficient. So imagine if I had a 3 here, then you would just write 3 down here. This one's different because it's the natural log of a variable. That's the key difference. All right, so if I want dy dx alone, what's the next thing I got to do? Yeah, we had to divide both sides by 1 over y, or equivalently, I can just say times y on the left and the right. So let's see what happens whenever I do that. So I get dy dx is equal to the natural log of 17 times y on one side and then everything else on the right. However, am I done with this problem? Why am I not done with this problem? Yeah, look at my instructions. I want to give my final answer only in terms of x. So the first thing I'm going to notice, I'm not going to be moving anything left or right anymore because my goal is still getting dy dx alone. But somehow I need to get rid of that y or rewrite it in some type of way so that I only have x. So is there any way that I can rewrite this y? How could I get rid of, or in other words, rewrite the y value? It has nothing to do with a trig function. I claim the answer is already on the board, a way to get rid of y and make it only x's. Yeah, we know y is 17 to the x. So I can just replace that y with 17 to the x power. And now my answer doesn't have any more y's. It's a derivative completely in terms of x on the right side. So if I have y is equal to 17 to the x power, the derivative of that is natural log of 17 times on 17 to the x power. So actually what we've done here is going to become a common pattern. Taking the natural log of the left and the right, using some log properties as needed, and then doing some implicit differentiation, and then replacing my y with the original function so that I get it in terms of x only. All right, so any questions about example number 8 before we move on from here? All right, so I'm going to go ahead and move forth. Hopefully this little arrow thing stays for the next slide. I guess we'll find out in a second. If the slide wants to go. Oops. I'm not too sure. Let me see what's going on with that. Ooh, that's not pretty. Definitely not what I want. So let me go ahead and try to reset this. And more or less, let me just try one thing real quick to see if it'll work or not. Just whenever I thought the board was working perfectly today. All right, let me go ahead, reopen this. Let's see, is there a way? I guess we will make do with this weird thing. See if I can get rid of that AE symbol. So it looks like this is the only one that got corrupted somehow. Let me just remove that. That works. All right, so let's go back to slideshow. Start from current, and then the arrow's gone. So I have example 9. Find the derivative if I have y is equal to x plus 3 to the 12th power divided by what? We had x minus 2 to the 10th power. Again, I want my final answer to only have x's. Let's see if I can make this show up. So looking at this problem, it doesn't look like we really need to do logarithmic differentiation. But why might log differentiation be helpful? If I didn't know anything about the logarithms, what rules would I need to take the derivative of this function? We have power rule, we have quotient rule, and then technically we also have some chain rule going on. 2 chain rules, if we want to be exact. So does all of those methods work? Yes, it would still work out, but we know that it can probably be a bit tedious going through all of these chain rules with quotient rule and power rules. So let's see what happens if I try my log differentiation. So to start me off, let's go ahead and put the natural log of the left and the right. So if I do that, let's see, are you going to show up? There we are. So I'm going to do the natural log of y is equal to the natural log of this big one on the right. So right now, it looks like, why did I make this look a lot worse than where I started? But this is going to clean up really nicely for us. So on the left, there's nothing I can do. Natural log of a single term, I'm going to keep that the same. On the right side, I'm going to try to break this down into several smaller log values. So the first thing I'm noticing on the right is that I have the logarithm of a quotient. If I try to split a quotient, what does that become whenever I try to split it into 2 separate parts? Does it become addition? Does it become subtraction? What's going on for that based off those old properties I gave y'all? Yeah, it's going to become subtraction, in other words, on the outside. In other words, I can rewrite this as natural log of the top minus the natural log of the bottom, x minus 2 to the 10th power. To the 10th. So that's using my quotient difference property of a logarithm. I'm going to keep on going here. There's one more property of a logarithm that I can use to take this even further. Which property can I use on the right side in particular? So looking at this first one, for example, how could I possibly rewrite that to make it a little bit better in the long run? Well, what can I do with a power inside a logarithm? Yeah, the power coefficient property. Since this is a log of something all to the same power of 12, I can go ahead and bring this 12 to the front. So 12 natural log of x plus 3. Minus, I'm going to do the same thing for the second part. I can bring down the 10. All right, 10 natural log of x minus 2. All right, so I applied the two properties of the logarithms. I haven't even done a derivative yet. So before I continue, any questions about how I rearranged this original function to be what I have down here? All right, so I'm going to go ahead and erase some of this so that I have space. I'm going to rewrite this bottom line here. So let's go ahead and erase this. And just rewriting what I had. Natural log of y was 12 natural log of x plus 3 minus 10 natural log of x minus 2. I claim that now I can go ahead and this might be a good spot for me to do some implicit differentiation. Because I got rid of that big quotient, I got rid of those huge powers. So starting on the left, natural log of y, we've already done this for the previous problem. So we're expecting it to be the same. I have 1 over y. And then by chain rule, we have times dy dx. So the exact same thing that we did for example 8 on the left. Now on the right, I have 12 is a coefficient. I'm not worried about that 12. What's the derivative of the natural log of x plus 3? There's a 1 in there. 1 over what? 1 over x plus 3. And then technically by chain rule, I need to multiply by the derivative of x plus 3. Derivative of x plus 3 is 1. So I'm not going to bother writing times 1 again. So this is the derivative of my first term here. And now I'm going to do the same thing for this right side. I have minus 10. Someone go ahead and give me the derivative of x, natural log of x minus 2. Yeah, 1 over x minus 2. If I want to be very exact, I should be multiplying by the derivative of x plus minus 2, but that's just times 1. This is great. We've done my derivative process. I still want dy dx alone. So on the left, I have 1 over y dy dx. I'm going to do the exact same thing as the previous problem. Let's multiply the left and the right by y. So on the left, I have times y, and then the right side, all of this times y. By multiplying by y, I get dy dx, that's still here on the left, perfect, is equal to, and I'm just going to clean up just slightly. I have 12 times 1, so 12 over x plus 3. You don't really have to simplify this for me, but I'm just multiplying because we know how to do 12 times 1 real quick. Same thing over here. I'm going to write it as minus 10 over x minus 2. And I have times y. But what can I replace my y with? I have this original thing up here. I can replace that y with this big function. So I can say that this is times, instead of y, x plus 3 to the 12th power all over x minus 2 to the 10th power. Giving me sort of an unsimplified answer, but it's all in terms of x. dy dx is equal to, within parentheses, 12 over x plus 3 minus 10 over x minus 2 times x plus 3 to the 12th over x minus 2 to the 10th power. These came from the derivative of my natural logs. This came from very directly, we know what y is. in terms of x. So we have our nice example 9. And as it turns out, if you did look at this problem from the beginning and you did not want to use log differentiation, let's say you did want to use a quotient rule with the 2 chain rules, you'll get something that's equivalent to this. It might look a little bit different because you would have to simplify it and make sure that they're equal, but it should be the same expression, assuming that we went through and didn't accidentally forget any pluses or minuses. But yeah, another application of log differentiation. Any questions, comments, or concerns about this one right here? All right, so let's go to example 10. I believe there's 11 examples I have total. So I believe we have 2 more left if I remember correctly. So let's see. Oop, and it crashed again. I guess that was expected. Do I want to recover it? No, let's just start from the beginning. So again, all of these things that we're doing is we're exploiting the properties of the logarithm in order to get sort of a more straightforward derivative. Oh, I lied. There's only one more example. So let me go ahead and make this full screen. Let me remove that dot. Out. Yes, every day I'm trying to fix one thing from these slides that doesn't want to work here. I think we did. Yeah, we just did example 9. Because example 8 was at 17 to the x. So example 10. So far, we've had x to a constant power. And then we also talked more recently, a constant to the x power. Now, what if I have a variable to a variable power? Something like this. X to the cosine of x, where cosine of x is my power. So again, looking at this problem, without looking at log differentiation, we don't really have any method that would let us tackle this type of problem. I definitely can't just use a quick power rule, because power rule only works for x to a number power. We can't really use something like a constant to an x power, like 17 to the x, because we have x in the base and in the power. However, using log differentiation, as you can probably expect, we're going to be able to solve this problem and get the derivative. All right, so once again, I'm going to go ahead and start by taking the natural log of the left and the right, just like before. And I'm going to see if I can fit all this on 1. So natural log of y is equal to the natural log of x to the cosine of x power. What property of logarithms can I apply here? Yeah, power to coefficient. This is a power inside the logarithm. I can go ahead and take it and make it into a quote-unquote coefficient. I'm saying quote-unquote coefficient because it's not really a coefficient as we usually think of it. But regardless, we can bring it outside of the natural log. So really, I can write this as natural log of y is equal to cosine of x times the natural log of x. And now I claim that we can go ahead and actually try to take the derivative of this expression. On the left, I think we can expect what's going to happen on the left side. What's the derivative of the natural log of y again? 1 over y, and then dy dx. The good thing about this, the problems that we're encountering, the left side is pretty much always going to look the same. We're not really expecting things to change on the left here. On the right, what rule or rules am I going to end up using here? Yeah, we need the derivative of cosine. We need a derivative of the logarithm. What other rule are we going to need? There's one more very important rule that's going to be used here. Let's see. Yeah, we have a product rule because this two things being multiplied together. It's a product. So I need the product rule. So just for notes, I'm going to identify this as the first and then this other one as my second. So following through with the product rule, we have the first, cosine of x, times the d second. What's my d second, by the way? Yeah, we have 1 over x. We know that the derivative of the natural log of x is 1 over x. So I have first d second plus the second. So I do plus, copying down the second term. And what's the derivative of the first? Yeah, we know that the derivative of cosine of x is negative sine of x. So I just did and completed my implicit differentiation portion. So what's going to happen next from here, probably? Yeah, multiply by y, and then we're going to replace that y with whatever it was in the beginning. So, because I'm losing space here, let me just write down the final answer. Dy dx is equal to, and this is not something that you necessarily have to do. I'm just going to write it for the sake of making it a little bit cleaner. Cosine of x times 1 over x. That's just cosine of x all over x. Natural log of x times negative sine of x. There's not much I can do there. I'm going to write as natural log of x sine of x, putting the negative up front. And then times y. But we know y is x to the cosine of x power, giving me my final answer. Dy dx is equal to cosine of x over x minus natural log of x times sine of x times x to the cosine of x power. So the answer looks very busy and everything like that, but individually our steps boil down to product rule and then derivative of cosine, derivative of the natural log of x. So those were what this problem really boiled down into, I guess with a layer of the log differentiation as well. So one thing generally about this problem, or problems in general, is that there are times when log differentiation can be really helpful, like what we had here, or in the previous two examples. And then there's other times where we don't really need it. So part of the problem is making sure when does log differentiation really help us. And then that's something that you'll have to sort of play around and get used to, looking at the problem, maybe some trial and error, seeing does this work out or not. Like for example, if I gave you something like y, oops, that's weird, y is equal to 3x squared, you don't really need log differentiation for that, for example, because we have rules for that already. We have power rule. But for stuff that's a little bit more complex, log differentiation can be helpful. Sometimes it might be more complicated, but it really depends on the problem. All right, so that is our example 10, talking about the derivative of y is equal to x cosine of x, where cosine of x is the power. Any questions about what we did for example 10? Oh, I was just saying that was an example on where we don't need log differentiation. I was saying that sometimes log differentiation really good, nice. Other times, like right here, you're probably not going to put natural log on the left and the right. Could you? Yes, you could. Uh, yeah, it's not really necessary. And technically, for those all these problems, well, for 8 and 9, you could have probably worked through them without log differentiation if you were doing some little clever methods. But in this one, based off any of our rules, then there wasn't much we can do without log differentiation. Primarily because we never saw x to an x power. We saw a number to the x or x to a number power. All right, so this is example 10. All right, so besides that, now we're done with this section. The next thing I just want to talk about real quick is what's going to happen for our next exam. So what I'm thinking is having an exam, let's say a week from today on today's Tuesday. So next Tuesday. Obviously, I haven't made y'all's exam yet, but I will be posting y'all study guide pretty soon on Blackboard. And I'll probably post a solution sometime this weekend and stuff like that. But that's stuff that y'all can all expect. We'll probably, let's see, I just gotta think real quick what we're gonna be doing for the next 2 days on Wednesday and Thursday. I could post a homework, but I think I'd rather have y'all focus on doing the study guide and going through that rather than getting an assignment turned in. But yeah, that's just something that I wanted to announce, making sure that everyone's on the same page that an exam is coming up a week from today. All right, besides that, I'll let y'all go. We are out a fair bit early today. All right, I'll see y'all tomorrow. I'm gonna go ahead and end the live stream in just a moment. Discard that. All right, let's go ahead and end it.
Oh yeah, that live stream was free.